Okay, we're going to look at our fourth set of problems, okay, which again utilizes several different tricks. For the first one, it is an algebra trick, okay. I ideally want to do a u substitution where u is my denominator, but the derivative of that is not present in the numerator. So what I'm going to do is I'm going to add and subtract the same term on top and bottom, or add and subtract the same term in the top, okay. Now, why did I choose that term? Well, because now this first two pieces are a multiple of my denominator. So when I divide it out, I'm left with 2 minus twice e to the negative x over e to the negative x plus 1 dx. Now I can do my u substitution, where u is my denominator. du is then minus e to the minus x dx, which I have present. So my integral becomes 2 plus 2 over u du. Okay. Antiderivative is 2 plus twice ln of the absolute value of u, and then of course I have to remember to undo my substitution for my final result. For my second one, it is a u substitution, but it's a somewhat complicated u substitution, because at first guess you might think u should be x squared. But if you let u equal x squared, we'd want this x in the numerator instead. So I'm going to let u equal ln of x squared. Then to find du, I have to use chain rule. It's 1 over the inside times the derivative of the inside times dx. Okay. This cleans up to 2 over x dx, which is almost what I have present right here. And so I bring the 2 over to solve for what I have. Then my integral becomes the integral of 1/2 u du. Okay. So that has an antiderivative of 1/4 u to the 4th plus c, and then of course I have to undo my u substitution. Excuse me, u squared. Antiderivative of u is 1/2 u squared. Okay. For my third problem, it is again a u substitution. This time the u is fairly obvious. It is the inside of the trigonometric function. Remember, we're thinking of this as 2 times x to the minus 1. So du is negative 2x to the negative 2, okay, otherwise known as negative 2 over x squared, which is almost what I have, except for I'm going to move over the negative 2. My integral then becomes the integral of minus 1/2 tangent of u du. Now, the antiderivative tangent is a formula we learned back in chapter 4. It is minus ln of the absolute value of cosine, but that minus cancels with this one, leaving us 1/2 ln of the absolute value of cosine u plus c, and then we undo our substitution by plugging in 2 over x. Okay. For our final example, this is going to be quite a lot of work algebraically, because what we want to do is complete the square on this in the hopes that it will turn into an inverse trigonometric formula we know. So to complete the square, I'm first going to kick over the plus 3 to make room. Then I'm going to pull out a 4 that these two terms have in common. Okay. All right, now to make this inside a perfect square, I'd have to put a plus 1 here. But since it was inside it times by 4, what I really added was 4, so then I have to subtract 4 as well to counteract it. This then becomes 4 times x minus 1 squared minus 1. And that can go into my integral. Okay. Now, as we expected, this is an actual inverse trigonometric formula. Okay. In fact, it's arcsecant. Okay. Because we have something squared that matches right here. Now, technically speaking, we'd want a 2 right here. And to counteract that, we're going to multiply by 2. So that then this term squared is that term. Okay. So this then becomes, carry the 2 along for the ride, arcsecant of 2 times x minus 1 plus c. Okay. Excuse me, should be absolute values. Okay. For our final answer.